This program is the first of a two-part guide to the properties of every material in the known universe. Astronomers have examined the light and other electromagnetic radiations coming from distant galaxies using very sensitive spectrographs. They have found that the planets, stars, moons and even the asteroids and comets that inhabit the universe all exhibit the spectra of the atoms that make up the Earth. The stuff of the cosmos may be heated to millions of degrees and compressed to incredible density. It may be frozen near absolute zero in the vacuum of space, yet everywhere the building blocks, the atoms, are the same as those on Earth. Think of the variety of materials in our garbage. The cosmic stuff that we throw away as junk is mind-boggling in its variety. Our claim to an understanding of every material seems like a wild exaggeration. Yet, the science of chemistry is a powerful index. It reduces vast complexity by systematic classification of substances. The first distinction chemistry makes is according to atomic composition. Most substances in the world around us are mixtures, different kinds of atoms in variable ratio to one another. Mixtures are a blend of different chemicals, so their properties vary. Pure substances have a fixed and definite atomic composition, which gives them a unique set of properties like melting point, colour or solubility. A pure substance can be all the same kind of atom and called an element, or made of different kinds of atoms combined in a fixed ratio called a compound. More than 5 million pure substances have been found in nature or synthesized by chemists. Those pure substances composed of one type of atom only are the elements. Chemists have arranged the 106 atom types into the periodic table of elements. 89 of these elements have been found in nature, and the rest have been synthesized in nuclear bombardment reactions. The periodic table groups elements with similar electron configurations and therefore similar properties into columns. Each column contains a family of elements. Chemists think of pure substances as neutral atoms or charged atoms, called ions, in a well-defined structure. The repeating structural unit can be one atom or a number of atoms or ions bonded together. This level of classification is a very useful index. This table sets out the properties of differently bonded substances. Changes of state, solubility and conductivity are properties that involve the forces between atoms, ions, molecules and their electrons. As we build up the table by looking at bonding types over 2 programs, our chemical understanding and ability to predict any chemical's properties will grow. When a bond forms, energy is released, and a more stable system with lower energy is produced. The formation of a bond can be thought of as the resolution of the basic electrostatic forces between the electrons and protons in the atoms. However, these interactions are quantum mechanical. They aren't always straightforward. One quantum mechanical premise is that a pair of electrons is very stable. When 2 hydrogen atoms, each with an unpaired single electron, approach one another, a covalent bond forms as the electrons pair up. Each atom shares the electron pair and becomes part of a molecule. Hydrogen gas is just an enormous number of hydrogen molecules. No bond at all forms between helium atoms because each atom already contains a pair of electrons. Helium is a stable monatomic gas that rarely bonds at all, and so are all the inert or noble gases, which is why we have left them off a periodic table showing trends in electronegativity. Electronegativity is the power of an atom to attract electrons to itself. It increases from left to right along a row or period, and from bottom to top up a column or group. So, fluorine is the most electronegative element, and francium, apart from being radioactive, would be the least. Atoms with the same or similar electronegativity can best achieve stability by sharing electrons. If the sharing is equal, as it is in the hydrogen molecule, then the electron density is uniform or even. This type of covalent bond is described as non-polar. If the atoms are different, say hydrogen and chlorine, then the sharing is unequal. The electron density is shifted towards chlorine and a partial charge separation is set up. Hydrogen chloride gas and this type of bond are described as polar. Each molecule is a tiny dipole. When the electronegativities differ greatly, like sodium and chlorine, the electron is completely transferred from one atom to another. All covalent bonds belong on a scale between these boundaries. In sodium chloride, there is no electron sharing. The two constituent atoms have such different electronegativities that all the atoms form ions, and the bonding is called ionic. Here are the relative sizes of monatomic ions, in orange, and the neutral atoms they're derived from, in green. To the left of carbon are cations, positively charged. They are always smaller than the neutral atom that has lost electrons to form them. Anions, on the other hand, are negative ions, formed by elements to the right of carbon. They're always larger than the parent neutral atom that gained one or more electrons. Ionic bonds form when electrostatic binding energy is released, as an anion and cation are attracted. The result is a network ionic solid called a salt. Salts are a geometric array or crystal lattice of positive and negative ions. The majority of salts are white crystals or powders when pure, although some are coloured. The strength of ionic bonds depends on each ion's radius and the electrostatic charge. The bonds can be broken by heat energy. In this demonstration, a voltage is applied between a metal crucible filled with salt and a central electrode. As the salt melts and its ions become mobile, current begins to flow between the electrodes. A molten salt is a good conductor of electricity, a property shared by those materials that contain mobile or delocalized electrons. This is a strip of zinc metal, copper metal, bismuth, and a large piece of carbon in the form of graphite. Non-conductors have bound or localized electrons. This is sulfur, glass, and a piece of wood. What happens on the atomic scale when a salt dissolves in pure water? Notice that blue copper-2 sulfate turns the water blue. Think of the ions in sodium chloride. They form a regular, solid crystal lattice. Now, water molecules are polar. Each one acts like a tiny dipole, and in concert they can bring a salt's ions into solution as the opposite charges attract. Chemists write the process like this. They add a reverse arrow because after a while ions in solution are going to rejoin the crystal. All salts in dilute water solution completely dissociate into ions. A salt's solubility depends on the balance between the forward and backward reactions. These equilibria favour the right-hand side, so both salts are very soluble. Conductivity depends on mobile ions. This is pure water. Copper 2 sulfate solution and a sugar solution. In summary, ionic materials have high melting and boiling points. They are soluble in polar solvents, and they conduct electricity when their ions become mobile. Carbon, silicon, and oxygen atoms have almost identical power to attract electrons. They fill their outer orbitals by sharing electrons with each other, and the result is covalent network molecular solids like elemental carbon. Graphite is one network formation, or allotrope of carbon, with distinct layers. The other form is the highly symmetrical and strong structure of diamond. Another network molecular solid is silicon dioxide, known as quartz or silica. These materials are all an infinite array of atoms in a giant molecule that is literally as large as the crystal. 3/4 of all the atoms in the Earth's crust are either oxygen or silicon atoms. They are the main elements in rocks and minerals, where they occur with a range of metal cations as metal silicates and alone as quartz. Covalent network solids are very strong, very resistant and insoluble. So it's no surprise that after endless crushing and mixing or erosion of rocks, the result is sand. Tiny quartz crystals containing a variety of impurities. Sand is used in the manufacture of a hard, brittle and transparent mixture of silicates that is valued precisely because it is so unreactive and insoluble. In our table, covalent network bonding forms a clear group. These materials have very high melting and boiling points and are virtually inert. Graphite is the only material in the group that conducts electricity because electrons between its layers are spread out, but electrons in covalent bonds are nearly all localized and immobile. As a rule, covalent materials do not conduct. Alkanes are a series of hydrocarbon compounds whose atoms have similar electronegativities. The simplest alkane is methane, a small molecule that exists as a gas at room temperature. In the molecule, hydrogen atoms share their electron with 4 electrons from a central carbon atom. The spatial distribution of 4 bonding electron pairs determines the molecule's tetrahedral shape and tetrahedral bond angle of 109.5 degrees. This shape is a useful instructor when deducing the shapes of related molecules made up of neighbouring atoms in the periodic table. In ammonia, a lone pair of electrons from nitrogen takes the place of one hydrogen atom, so the molecule is shaped like a pyramid. In water, two lone pairs from oxygen replace two hydrogen atoms. The water molecule is bent because it results from a tetrahedral distribution of bonds and electron pairs around the central oxygen atom. Once this relationship between methane, ammonia, water and hydrogen fluoride is understood, then the approximate shape of molecules made of atoms in the same group can be inferred. Covalent molecular bonding is also the bonding in a number of polyatomic ions. This is the ammonium ion, and these are the sulfate and nitrate ions. If two pairs of electrons are shared between atoms of the same or very similar electronegativity, a double covalent bond is formed. Triple bonds are also possible. This is an acetylene or ethine molecule. Carbon dioxide is a linear molecule that freezes into a solid known as dry ice. The solid is a molecular crystal with a cubic symmetry. Dry ice sublimes, which means it misses the liquid phase and turns from a solid into a gas as it warms under normal pressure. It also reacts with water, producing carbonic acid. Here, an initially basic water solution containing universal indicator is neutralized and then eventually turned acidic by carbonic acid. Many modern materials are molecular chains or polymers. A large number of links, called monomers, join together to form a macromolecule. The bonding is covalent, both within the links and between them. This is raw nylon, a polyamide that forms spontaneously at the interface of two solutions. Wood is mostly cellulose, a polymer of glucose. The natural world is a showcase for the properties of polymers. Think of almost any biological tissue, any growth process, and polymers are at the heart of the raw materials and even the organizational blueprint. The major classes of organic compounds associated with life are carbohydrates, proteins, lipids or fats, and nucleic acids. These are polymer materials. They are long chain molecules whose spiraling, folding and bunching determine subtle and diverse properties. Yet the links of the chain contain ordinary atoms of carbon, hydrogen, oxygen and nitrogen. Chemists know that these atoms have almost the same electronegativities. They understand that these particular atoms make themselves stable by sharing electrons and bonding covalently.